we'll start the stream again. And don't worry, it doesn't pick up any of your voices. So if you're skittish about, having your question immortalized, don't worry, it won't. Before break, someone helpfully pointed out a typo here. This ICC should be a 1. My bad. I wish I could say that I planned that as a learning opportunity for you, but I'm not that good. So yeah, cross that out. That's just a copy-paste error. All right. So lots and lots of terminology. Here's some more. So introducing then how time plays a role in these things. I'm starting with an example with just linear time. It could be time in study. It could also be time. It could be any other kind of time. But the idea then is just to introduce what fixed versus random means. That's the big picture. So 2 different questions about possible effects of time. And one is answerable by any kind of repeated measures ANOVA. Is there an effect of time on average? So in other words, if you have a line connecting the sample means over time, is that line something other than flat? If so, we would say that you need a fixed effect of time. So this is slide 21 in lecture 1 here. The more interesting question, and the part that ANOVA cannot buy you, is does the average effect of time vary over individuals? In other words, do people need their own version of it? And if so, then you have a random effect of time. So fixed means everybody gets the same. Random means everybody gets their own. So here are examples of what the models would look like if we have just linear time to start with, which is where everyone starts because that's the easiest one. So here are some pictures in which each figure has a random intercept. And the first picture here is an example of neither a fixed effect of time nor a random effect of time. So the x-axis here is time, y is your outcome. The heavy black line is meant to indicate the sample means, and these are individual trajectories. And we do not have a fixed effect of time because the average line is flat. And we do not have a random effect of time because that flat line works for everybody. There is no change, and no change is the same. And speaking of the tie between interclass correlation and something like this, I didn't draw the little dots around here, but so long as there is variation over time, your ICC will pick that up. Whether or not that variation is related to a systematic effect of time, that's a separate question. So let me share with you a cautionary tale. The second time that I got to teach this class, I was a postdoc at Penn State, and at that point I had all of the students use their own data for class assignments, and their very first assignment was to calculate an ICC and to make pictures like this one. And one of my students had an ICC of 0.99999999999, and I went, oh no. So I asked to talk to him, and I said, dude, this is not going to work. An ICC of 1, what does that mean, folks? Yeah, no within, all between. And he was going to be the first person in his field to do a longitudinal analysis of blah, blah, blah. I'm like, dude, no, you're not. You do not have longitudinal data. Your people told you the exact same thing every time. And his spaghetti plot, as it's called, looked exactly like this. And I don't know what happened to him because he dropped the class, and I never heard from him again. And I felt bad about that until I realized that we were having this conversation in late January, and we were not having this conversation at his final. Struggled to describe why he couldn't find any within-person effects. So you have to have within-person information variability as a logical prerequisite to finding any within-person effects. So long as your interclass correlation is less than 1, play ball. You can also have an interclass correlation of 0, and that's okay too. That can happen when people really don't differ from each other on average, and all of the action is longitudinal, in which case a cross-sectional study would be relatively uninformative for what you're studying. But so long as you have within-person information, that within-person information doesn't necessarily have to lend itself to systematic change over time. So this picture would be if I didn't have a significant fixed effect of time nor a significant random effect of time, what I would describe this as is fluctuation. There is information across time to the extent that your interclass correlation is less than 1, but it's not time specific. It doesn't matter if it's time 1 or time 2 or time 3. Another one then is, yes, we have a fixed effective time, but no random effect. So in this case, there is systematic change. On average, people are increasing, but everybody is increasing to the same extent. They don't need their own. And so these two pictures are the only situation in which the typical approach to repeated measures ANOVA would be applicable, because they both feature parallel growth, no random effects of time. And this parallel growth pattern implies that having a random intercept only, or what is known as compound symmetry in the stats terms, is going to be sufficient, that the variance doesn't change over time, and the covariance doesn't change over time either. More interesting case is this one. Let's say that you are working on your dissertation and you were silly enough to do a longitudinal study for your dissertation. Anyone silly enough to mention that? No? Okay. Yeah. Oh, you're silly enough, right? Let's just say hypothetically that you spent 2 years collecting longitudinal data, and you finally get it all in and you get it all entered and you're ready to sit down and you throw it into an ANOVA and you have no main effective time. And you might go cry, go drown your sorrows in wine or ice cream or your poison of choice. But if you came to me, I would say, well, the game's not over. Because what if you actually had a pattern like this? This picture shows no fixed effective time, which would be no main effective time in ANOVA language, but that's because some people got better and some people got worse. There is a random effective time. People need their own version of the slope. And if this was a treatment study, you might want to know who are the people that I made better and who are the people that I made worse. And you would be able to predict differences in growth or decline as a function of person-level information. And then you can have both. And this is probably the most common scenario in within-person change types of studies, where you do have an effect on average and you also have random differences around it. People need their own of the effect. And I'm talking about time in this instance, but these same sorts of constructs apply to any kind of time-varying covariate. Any variable that you've measured over time, you have the potential to have fixed and random effects for. Time is just a time-varying predictor. So what if you had something like stress and well-being? Measure those repeatedly across days. To the extent that when people feel more stressed than usual, they feel crappier than usual, that would be a fixed effect to the extent that it shows as a general tendency. But people might also vary in their resilience. So the extent to which feeling more stressed than usual makes you feel crappier than usual might vary randomly over people. So that would be a random effect of stress in predicting well-being, in the same way that we could have a random effect of time predicting well-being. So fixed and random as a concept, much more general than just time. Fixed means there is an effect that everyone in the sample shares, but in addition to that, random is an effect that each person gets their own of. We estimate a variance around the fixed effect. And so because you can have both, neither, or either, having a non-significant fixed effect does not preclude you from testing the random effect that goes around it, because you could be in this C cell over here. So what the models then would look like, the empty model that we looked at first before break, this one right here, that's the A cell. That's what that model would predict. The empty model predicts this. To move over to B, we pick up a fixed effect of time. So here I have now 2 beta placeholders in my level 1 equation. Because I have 2 betas at level 1, I have 2 betas at level 2. You always have as many level 2 equations as you have placeholders in level 1. So I'm using beta as my placeholder here. So beta 0I is still how each person gets their own intercept, and it's a combination of fixed plus random. The difference is that this fixed intercept now carries a different interpretation. The intercept in any model is always the expected outcome when the predictors are 0. If I don't have any predictors, the intercept is the mean. Once I pick up predictors, like here, this is now the expected mean from drawing a line through the data, the expected mean given a linear model of time at time 0. So this implies that we have centered time, meaning we have subtracted or added a constant such that 0 means something. Now, there are no wrong ways to center, only weird. You can not center, and you will get the same predicted values, the same model fit, the same whatever. The reason to center is to change the interpretation of your parameters. I have seen models not converge when people have forgotten to center or picked times that are way outside the range of their data. So for instance, I used to work a lot with cognitive aging data, and I was helping someone troubleshoot a model where they were working with older adults in the sample of 80 to 100, and they forgot to center age. And the random intercept variance right here in the model blew up, because not only was she trying to have the model predict what the expected intercept for her cognitive aging outcome would be in newborns, time equals 0, but she was trying to predict the variance across the newborns, the random intercept variance. As you might imagine, it's kind of hard to predict baby differences from older adults. So in that case, the model did not work because of centering, but most of the time it won't be quite that bad. But we're presupposing that time 0 is somewhere within your data, wherever it is up to you. Here then we pick up a fixed linear slope only so far for beta 1, so everybody gets the same. So this model predicts this B cell right here. And that's shown a little more clearly with the composite model down here. Now random, one new term. Can you find it? We'll play Where's Waldo with the equation. What's new? Random linear time slope. I love your accent, by the way. Statistics sounds a lot more friendly with the southern accent, doesn't it? Here it is, folks. Yep, you won. What do we win? Job security. You know, I make that joke a lot, but I'm actually not joking. If you learn this stuff, someone will always be willing to pay you who does not want to learn it. Always. Amen. It's true. No matter what you came to school for, if you learn statistics and you become conversant in this language, you will always have a job for that reason alone. So, yes, you won is what you win. So this works the same way as the intercept. Gamma 1O here is the fixed slope for the average effective time. U1 is how far off my effective time is from that average. So fixed plus random gets me mine in terms of the intercept, and now also in terms of linear time. So we'll talk about time this morning, and we'll talk about other types of time-varying information this afternoon. But in adding this U1, what's not showing up in these equations, but also is going to be part of the model, is a covariance. Because where I am at time 0 is likely to be related to how much I change. And that, speaking of job security, is not a default in any software package. All the packages have the U0s and the U1s be uncorrelated as a default, but they both go to the same person, so that's insane. If you set it up as an SEM, yes. If you set it up as an MLM, no. Yes. Yes, the ins and outs of what the defaults are quite amusing to me, but yes. That's why in the code that you'll see, I write out everything. I write out every parameter, whether it's default or not, because I want to know what I put in there. Yes, and they change the defaults, and so then your code may or may not work in the next version, so yes. But so we're picking up a U1, we're also picking up a covariance between the two. And so then this model gets us to either of these C or D pictures. The C picture would be if the fixed effective time was there and not significant. The D picture would be if it were there and significant. So to show those a little more graphically then, here's slide 25. So note time here, time 0 is at the beginning. The heavy black line is for the sample means, and the blue one is for me. And note that because I have more than 2 occasions, I have the chance to have both different lines, different slopes for different folks, and residuals being off the line. That only happens if you have 3 or more occasions per person. So starting off here, gamma 0, 0, that's my fixed intercept. That's my expected outcome predicted by the model at time 0. So I'm making that distinction. This is not the actual mean at time 0. This is the one predicted by a straight line. So it's the end of the line here. That's my fixed intercept, and that's 10. But I am starting out lower than everybody else. So U0 is my random intercept. My random intercept is a -4, and that gets down to where my line predicts that I start, which is at 6. U's are always how far off you are. What they are off from is the fixed effect. Then the slope. The slope of the black line is gamma 1, 0. That's in 8th grade algebra language, rise over run. Remember? Delta y, delta x, etc. That's 6. But I am growing faster than everybody else. So I get my own slope deviation via U1. My slope is more positive by 2. So my U1 is 2, which gets me to my full slope of 8. So 6 is the part that everybody shares. A plus 2 is my U1. And then now that I have 3 or more occasions, even though I have my own slope, it's not going to fit my dots perfectly, so E is what's left. So here's an E here, there would be a positive E here, near 0 E here, and a negative E here. So E becomes, why are you off your line today? I gave you your own line, isn't that good enough? Well, there's lots of reasons. Maybe something bad happened that day, or maybe not. You don't want a straight line, you want a bendy line. But E is now this remaining within person information. So part of what was E, part of what was why are you off your line, has actually been moved and renamed. U1, part of the reason why you might have been off your line is because you needed a different line than other people. So U1, that new term, is a variance across people at level 2. So to put that into what it's going to look like on your output, what we are saying then about dependency is different than what we were saying before. Before, we only had a random intercept. We only let people differ from each other in one way, in constant mean differences, and that was it. Now we are saying there are 2 reasons people differ from each other. There are 2 kinds of person dependency, constant mean differences and constant slope differences. So it's between person variance in a within person effect of time. So I'll say that again because the language gets tricky. So we have added a between person variance at level 2 in a within person effect of time, where time is level 1. So the level 1 effect of time varies randomly over people at level 2. Level 2 is between. So then over here is level 2 between. Yes.
So the idea is we think about it, so it's because a
yeah, each person has one U0 value and one U1 value, and that creates their pattern of data. And so U0 is a between-person level 2 random intercept variance. U1 is a between-person level 2 random time slope variance. So people differ from each other in two different ways. And because the U's come from the same person at level 2, they get a covariance. So any random effects that come from the same unit get a covariance. So random effect is an umbrella term under which random intercept and random slopes are specific kinds. And it's easy to get somewhat lazy and unspecific in talking about random slopes when you only have one variable in the model, but that is quickly going to be insufficient. So more specifically, U1 is the random linear time slope. So we're saying then that the residuals from the same person were correlated for two reasons: intercept differences between people and time slope differences between people. And after both of those reasons have been taken into account, the E's that are left within persons have constant variance and no covariance. That's an empirical question, but that's what the model by default assumes unless you change it. How these get put back together again is a bit more complicated, but I want to show it to you because it helps to explain how multi-level models handle messy data. Have you heard that word before, handle? Multi-level models handle missing data and they handle unbalanced data. Do you know what the word handle means? Exactly. It's a word people use when they don't know what they're talking about. It is a hand-wavy word, right? It handles it. So the next time someone tells you that, you can ask them exactly how does it handle it, and then you can tell them this is how it handles it. But to do it requires a little bit of matrix stuff. So if you pick up a stats book, you will see the same thing that I've just been talking about written this way. The syntax, or excuse me, the notation is always author specific, so let me give you mine. Y is a matrix that holds the outcomes from the same person. So this is a model for one person's data. X is a matrix that holds the predictors that have fixed effects. So I get one column of ones for the fixed intercept. And here's my time variable here next to it. Gamma is a matrix that holds the fixed effect estimates themselves. And then in blue here, this is the model for the variance. So Z is the name of the matrix that holds predictors that have random effects. Here, X and Z are the same because both the intercept and the linear time slope have fixed and random effects. But not every fixed effect needs a random effect to go with it. U, then, is how far off your intercept is for U0, how far off your slope is for U1, and then E are the level 1 residuals. So it works out to be the same type of equation that you've seen before. But this Z thing right here plays an important role in how this handling function works. Z wraps around G to make it the right size to be added to R to get to your predicted V matrix. So V is the data put back together again. So here's the critical part. This part here in brackets, that's new. When we only had a random intercept, the total variance that was predicted at each occasion was partially due to between-person level 2 random intercept variance, partially due to within-person level 1 residual variance, and that was it. We've added this part in here, which comes from the random slope and its covariance with the intercept. What this does is it changes over time in a quadratic pattern, given the square term here. So this is cool for two reasons. Number one, if people change differently, variance has to change over time. People are going to spread out or they're going to get closer together. You know that has to be the case. This random slope for time is going to mimic that process. It's going to make the variance change over time, and it's going to make the covariance change over time. So now covariance is time specific too, and it's going to do it even when you have unbalanced data. So you can always, in balanced data, let each occasion have a different variance. You can just ask it. It's called a heterogeneous variance model. It's an H in the software after the options. But you can't do that in unbalanced data because you don't have a separate time value. Each time value can't have its own variance. You can't have a variance for all the 2.5s and the 2.6s and the 2.7s. It's too much. But what this function then does is it's capable of interpolating. It can interpolate what the variance would be at any time, the ones that you were supposed to have and the ones for the people who messed up and didn't come when they were supposed to. So it allows the variance to change over time. So non-constant variance is now the assumption of the model, and it doesn't need balance time to do it. Same with the covariance. It's capable of predicting variance and covariance at any time according to the model. So that means when you have people like this, here's how we put it back together again. On slide 29 here, I have two people's data. This is what the software is actually doing for you behind the scenes. It's building these ginormous block diagonal matrices, where block diagonal means like stuff and then zeros and then like more stuff and then zeros. So here's the data for one person who came all 4 occasions and they came exactly when they were supposed to. They have their unique random intercept and random slope information for their intercept and their time slope, a common shared random intercept and slope variance. There's their information sideways, and a common shared e-variance. That combined gives this person their very own V-matrix. If everybody has complete data and balanced data, everybody's V-matrix looks exactly the same. The second person here, not only did they not come when they were supposed to, they came at time 0.2, 1.4, and 3.5, but they didn't come 4 times. Their data are both incomplete and unbalanced. No worry. We stick in whatever data they gave us, work with a common random intercept and slope variance, a common residual variance, and they get their own V-matrix. Their own V-matrix is going to know which occasions they actually have and that there's only 3 of them. So this person's V is going to be a 3 by 3, this person's V is a 4 by 4, and it goes on and on. So how it handles missing data and how it handles unbalanced data, the magic really is in this Z-matrix. The model understands when each person was there, and it's capable of building a prediction for each person's unique pattern of variance and covariance based on their unique values of time. Ta-da! Now the off-diagonal part. Do you know why there's like zeros stuck everywhere here? You did. Yeah, you asked me earlier. Say it again what you asked me. Do you know? No. You said that now we're back to independence and stuff like that, right? Okay, say that again. Now we're back to independence assumptions, right? Yep. All these are over here because people are unrelated according to this model. And what happens if we need, if the assumption that the E's are unrelated is not possible? So in longer long-term data, if you have more than 4 occasions, you might have an extra residual correlation that you need. No worries, stick it in here. Change this structure to something that includes an AR1. But the correlation between persons is also built through the random effects here, and that's what we'll see in our example more specifically. So yeah, people are independent, but what if they're not? What if you have a clustered sample such that people come from groups? Well, you stick something over here that allows people from the same group to be related. And then you end up with a V-matrix per group instead of per person, but it works the same. Yes, sir? Before we complicate it that way, if I understand this correct, the parameters are still the same across these different... Yep. Between the person who came on time and the person who came on their own schedule. Yep. It's just that the only thing different is how many times they came with the exact time. Yep. Yes, that's exactly right. So he was saying this G-matrix right here, these level 2 random effect variances and covariances, these 3 numbers are shared all the way across the sample. Likewise, this residual variance right here is shared across all the occasions and all the people. Now that is also a testable hypothesis. And testing that kind of hypothesis has become increasingly possible in recent years due to software advances. Models that allow the amount of variance to change across persons or occasions are what's known as location scale models. Say that again, it's location scale is the thing to ask the Google about. I talk about those briefly at the end of chapters 7 and 8. They're heterogeneous variance models. So for instance, what if this first person was in the control group and this second person was in the treatment? Well, if your treatment affects people differently, then you might have more intercept and slope heterogeneity in the treatment group than in the control group. That's pretty straightforward to add as a predictor in the model that allows these G matrices to differ by groups. It would be a multiple group approach in SEM. It would also be a group equals option within either Stata or SAS. You can do it a little bit in SPSS, but it gets limited quickly. Likewise, if you wanted to have a different residual variance across group, you could do that too. Now, where this starts to get more complicated is if you think about residual variance differing randomly across people, such as in a fluctuation study. And in that case, you would actually want to predict why some people have more variability than others. And so I'd be happy to talk more about that if anyone's interested. But yes, the long answer to a simple question, these right now in the G matrix and in the R matrix are all the same 4 numbers. 1 intercept variance, 1 slope variance for time, 1 covariance, and 1 E variance that all these things share. Okay. Other questions? All right. Okay, at this point I have 2 choices for how to continue. I can talk about how this stuff would look in an SEM, or we could look at an example. Anybody have a preference? Example? Yep, okay. We're going to eject from the slide deck here. And the example that we're doing is actually after the end of all the slides in your other packet. It will 1A. So I made it so that all of the things that you would need to follow this discussion are in front of you in your packet. I have all the syntax and output that's annotated. However, if you'd like to run things along with me, in the download packet that I pointed to on my website, I have separate folders for each program, and you can find the syntax and output for those, as well as the full output for all of these models. So the output that I have in there is SAS output. SPSS output looks remarkably similar. SAS is just easier to work with in a more compact form, and it also has some extra things that you can print that are not possible in SPSS, which is why I don't use that as frequently in workshops. But this is what we're looking for. Did y'all find example 1? Okay, so there's example 1 as one set of data and models. I have 1A here because this is how you do all of the models in these programs. Your other packet then has the M+ version, which is in landscape instead of portrait, which is why it's in a separate packet. So we'll go over this first. So how many of you have tried to run multi-level models in one of these programs here? A lot of people? Okay, well then some of you will be familiar. I will go over how to do it in each program to the extent possible. If I skip anything or if you have questions about what it means, you can ask me. I also want to point out on the book's website, so the website for the book, it's called pilesofvariance.com. That's my shtick. Believe it or not, that was actually, this web domain was a birthday present from my husband. He bought me pilesofvariance.com. because I've been talking about how I wanted to have that be the book's website, so he got it for me. So I own that. But at the top of the example section, there's a file called General Notes About Program Syntax and Models by Chapter. And so within each of these, for instance, it's a written version of what all the options are, starting with just all of the examples in my code, how to get data in and out of things, how to do basic data manipulations, and then also within the mixed, what every single line means and what you're asking it to do. So this is meant to supplement all of the shorter annotations that I have, and so I wanted to make sure you see that. But these are data, simulated data from the book. I simulated them based on some data I had seen at Penn State, actually, so they're inspired by a real-life story. So this is data that we found in the second example of Chapter 7 and continued into Chapter 9. 200 girls measured approximately annually, so it's unbalanced time, meaning that we have a rounded version we can work with descriptively, but there's really no answer key in the sense that there's no common variance-covariance matrix to come back to. So they have risky behavior as the outcome in this example. We will also end up looking at a time invariant predictor for their mother's attitudes about smoking and drinking, which was collected at the beginning of my fake study here. So the data first needed to be stacked or converted from wide to long form. So they were stored in a way such that each row was a single person's data, and I'm converting them into a form in which each row is an occasion. And all programs have a mechanism by which to do that. Here's what it would look like in SAS. In SPSS, there's something called vars to cases that allows you to do this. So for instance, I'm making a new column called age from the previous columns that were age 12 to age 18. So those were separate variables. I'm storing them one row at a time and making a data set then where I have 7 rows of data per person instead of 1. And so I have then risky behavior as my outcome, monitoring as a time varying predictor we'll look at more later. And by far the easiest way to do this is stata, which has a reshape command, which is very nice, so long as your variables are named in a convenient way. I am centering time such that age 18 is my time 0, so it's actually the end of the study. In some cases, such as measuring deviant behavior, there's going to be the most variation at the end, and so that's going to be the reference point for the model, is the end of the study rather than the beginning. And another thing that each of these pieces of code does is select complete rows. So we'll talk more about this in a little while, but another common misconception about handling missing data is that somehow you get to keep cases that have missing data. You don't. In multi-level modeling software, the same rules apply as in software that uses least squares. Every row must be complete. Every row is an occasion, which means that, say, if you have somebody who has 3 out of 4 occasions, you get to keep the 3 out of 4 you have, but you don't get to keep the 4th that's incomplete. So to keep the sample constant across models, I'm selecting it so that each row is complete ahead of time. What else to do instead, we'll talk more about later, but there's no great answers to that. Okay, so any questions on the setup? Most of this is, other than the stacking, is just making new variables. Yes? I'm going to get to n+2. But I thought I would start here because I thought this might be more familiar, and these are the kinds of models univariately that you can fit in these software. So the first thing that I always try to do in longitudinal data is to get a sense of what the answer is. In balanced data, you can do this by fitting a saturated means model, meaning that each occasion gets its own mean, and what's known as an unstructured variance model. So this is just letting everything be what it wants. Given that I don't have balanced data, I'm using rounded time to do this for descriptive purposes. So this model has as many means as you have occasions. Each occasion gets a different variance, and all possible covariances are estimated across time. This model has a special name in SEM. Does anyone know what it is? No? It's called the saturated model, or the H1. It is the answer key. It is the best fitting model that you can have. It tells us what the patterns are that we're going to try and approximate with fixed and random effects of time. So I'm not going to do significance tests relative coming back to this because there isn't exact time in this case. It's not exactly 12, 13, 14, 15, but it still is useful for descriptive purposes to give me a sense of what I'm going to be looking for. So to do that, occasion goes into the model as a categorical predictor. So that's the class statement in SAS, the by statement in SPSS. It looks like a fixed factors box if you do the drop-downs, and it's I dot in Stata. So that tells the program to make dummy codes for me to fit n-1 for occasions, different fixed effects that allow all the occasion means to differ from each other. I just want to know what the means are. On the variance side then, I am using only one matrix and putting everything together. So this is a multivariate version of the model. It's not a multi-level model. I am not yet differentiating between and within person variance. I'm just looking at the overall data pattern for which I'm going to then try and approximate it with between and within person variance. So here's what it looks like. Without any random effects, all of the variability is in one place. So I have 7 occasions. On the diagonal of this R matrix is the variance at each occasion. So the variance at time 1 is 20, the variance at time 2, this is age 13, is 19, and so forth. And it looks like the variance decreases, but then it starts to increase over time. And so do the covariances. The correlations show a little bit more readily the pattern of relationship across time. So the occasions that are closer together on the first off diagonal do look a little more correlated, but still, even between occasion 1 and 7, there's still a sizable correlation there. So this is the pattern that we're going to try to model with random effects. That's what we're going to try to capture, is this pattern of changing variance over time and changing correlation over time. Meanwhile, on the other side of the model with respect to the fixed effects, treating occasion as categorical means that it makes one of them the reference. The default is the last in SPSS and in SAS. So 23 is my intercept, is actually occasion 18, and these are occasion-specific mean differences. The collection of 6 differences for my 7 occasions is right here. This is what would be known as an omnibus main effective time in ANOVA language. So this is the MANOVA approach to repeated measures, only using maximum likelihood instead of least squares, so that we can keep incomplete cases incomplete persons, excuse me. Here's the means themselves. And so here in pictures then is what the patterns are that we're going to try and approximate. So on the left, these are the means across time. So does this look sort of linear or a little bit bendy? What do you think? Well, a little bendy, I think. Yeah, a little bit. And over here on the y-axis is the variance across time. So in these data, people are getting more spread out at the older ages. So that's what we're trying to fit. So who was it who was asking me about specification searches? I was talking to over break. Where did you go? AR1? Who was I talking? No one wants to talk to me. That was you. Okay, yes. So if you have balanced data, this answer key is the best possible fitting model, and you can test whether any alternative, simpler version fits not worse. And that's how you know if you are good or not. And that's exactly what the chi-square means in SEM as a test of model fit. It's a likelihood ratio test comparing the best possible model against the one that you picked. So I'm not going to do that in this case because I don't have balanced data. And in general, you can't have tests of absolute fit without balanced data. Everybody has to share a common covariance matrix so that you can all agree on that's the answer and that you are comparing alternative models to that answer. I rounded time in order to get this just to be able to make these two pictures. Yeah.
So, looking at the variance table, that jump, would that also be an indication of the bending?
Mm-hmm.
So you've got, you're kind of moving along with a little bit of an increase, and then all of a sudden you see this quite dramatic shift up as they're spreading apart. So that non-linear increase in variance would also suggest, you know, an increasing gap that's quadratic.
Almost. Yeah, so to foreshadow, adding a random linear effect of time actually makes the variance change quadratically.
Right.
Yep, and if you add a random quadratic effect of time, that makes the variance change quartically. What's time to the fourth, whatever that is?
Time to the fourth.
Yeah, time to the fourthedly. So yeah, that's what we're going to find fits. But whenever, in terms of if you're just looking at your data and you see variance changing like this over time and mostly in one direction, dead giveaway that you've got a random slope for time in there. In fluctuation data, this may not be as relevant. You may not see any differences across time because time may not matter in fluctuation data. So now we'll see how these models approximate this. So starting with an empty model. Empty means random intercept, jumping off point.
Sorry, can you repeat something?
Yes.
That's their that giveaway?
Uh-huh.
That giveaway for us?
Right picture. When you see variance that increases or decreases mostly monotonically over time like this, dead giveaway that you have a random slope for time in your data. If you had only a random intercept, your variance would not change over time. Random intercept means everybody changes the same, so there's no reason why the variability would change over time. And given that the topic of the workshop is not exactly growth modeling, I'm purposefully trying to go through this a little more quickly than I typically would, but I'm happy to slow down and explain things if these are new concepts too. So I want it to be as useful as possible. All right. Okay. Then let's start building our patterns. So empty means random intercept. Always the starting point. Find out how much of your longitudinal data are actually longitudinal. So we're introducing a new line of syntax to do this, random. It's random in SPSS, it's random in SAS, and in Stata it's bar. I know, and you just have to know, like where the commas go. There's no indication as to like labels like this. Stata is tough, and it won't let you have capital letters. So I rebel by purposefully spelling it in uppercase whenever I refer to it. Just my own little way of fighting the power. But we're adding a random intercept. And in SAS and SPSS, you do have to type intercept. It is not a default. It is a default in Stata, so I don't have to type anything after person ID. Person ID is telling it how the rows from the same person are to be grouped together. It also shows up as a nesting variable here on the class statement and on the by statement. I do most of my modeling in SAS, and I've written little programs to simplify some of the calculations. So you don't need to worry about those unless you want to do this stuff in SAS. But the ODS statement here is just saving a piece of output with which to do calculations. I'll do them in Excel as well in your packet. I have example one here. You can see all of the calculations that I had the program do for me. in case you're using another program that doesn't do that. So here then is my empty means random intercept only model. So I've got 3 parameters, 1 fixed intercept, 1 random intercept variance, and 1 residual variance. So V tells you how the levels are put back together again. So I've got everything on one page here that forms the model for the variance. This row right here, that UN11, that's SAS's ever so helpful way of telling you in the unstructured G matrix at row 1, column 1, that's your random intercept variance. So for my risky behavior outcome, my random intercept variance is 10. I have tried to label this for you out here. This is not SAS, this is Proc Lesa helping you out here, since SAS is not labeling these things in any way that's useful. The other programs aren't much better. So if this is level 2 intercept variance, that must mean this is level 1 residual variance, which is 17. So if we go through our list of synonyms, the 10 is level 2, is random intercept, is between, and this intercept variance specifically is the variance that is cross-sectional, that is due to mean differences. Some of these girls are more riskier than others, the end. 17 then is the level 1 within person longitudinal variance around the person means, intra-individual variation and change. We don't know which it is yet. It's just a variance that has to do with time. It changes over time, fluctuates over time. So 10 is level 2, 17 is level 1. If you add 10 to 17, you get the 28 up here. So almost 11. We'll call that 11 and 17. And so note what the model is saying. It is saying the total variance at the first occasion is 28 because it's part level 2, the 10, part level 1, the 17. And that 28 holds all the way across time. So right now it's saying people differ from each other in their intercept, and that's it. It's also saying that there's only one reason why the residuals from the same person are related, and that's because of the intercept 2. And that's why the 10 shows up here to form the covariance. If you convert that covariance into a correlation, you get this. So this V matrix is not given in SPSS. It's one of the few things that it doesn't do, and I find it useful for pedagogical purposes to show you what the model is actually saying about the data. But this correlation right here has a special name to it. It is also the interclass correlation. So 10 over 10 plus 17 gives us an interclass correlation of about 0.39. So 39% of our total risky behavior variance is between persons, is level 2 differences in the intercept, is cross-sectional mean differences, would have been there had we sampled them once, 39%. The rest of it is within persons at level 1. I haven't gone over significance testing yet, but you can see that this is the one instance in which SAS will give you this test directly. SPSS does not state it does. It compares a model that has the random intercept variance, the 10, to a model that doesn't. And if this chi-square value is significant, then the 10 is bigger than 0. So this would be the significance test for whether you have constant person mean dependency. The effect size for it is the interclass correlation. So 39% is between, 39% is level 2, 39% is inter, And the fixed intercept then is down here. The average across time is 19 on this scale. So this model says no change whatsoever. It's our jumping off point. We know it's not going to fit well, but it provides a baseline against which to fit things that are going to fit better. Okay. With me so far? Any of that you want to hear again or differently? This? Yes. This is my fixed intercept. Right now, because time's not in the model, it is the mean of the person means. Now we're throwing time in the model, but only as a fixed effect first. So this is something that I deviate from other authors. For instance, Singer and Willett in their book, they throw the fixed and the random in at the same time. When you do this in software, such as M+, they throw the fixed and the random in at the same time. I don't like that, because if the model fits better with two new things in it, how do you know which one it was that made the model better? So I go one by one. This version of adding effects also lends itself to doing appropriate tests with REML instead of ML, which is something we're going to talk about a little bit later too. I'm in ML so that we get the same results across programs. So I have a new variable here. Age C18 to me means age centered at 18. I have an equation up here in which I am explicitly showing my centering. I find it helpful to do it this way so that your reader knows what time 0 is without having to remember from your method section. So I'm picking up a beta 1, by which each girl gets her own linear effective age, and that's now going to be defined in level 2 by only a fixed effect. So I'm adding just the fixed change right now. So still just a random intercept, so the model for the variance is the same, other than that it's going to become variance left over after controlling for fixed time. So because I have added a fixed effect, I don't have to do anything more complicated than stare at the p-value that shows up on the output. Stare at the p-value, by the way you would talk about that in a manuscript is that is a walled test. Some people would yell at me for calling it a walled test with a t-value instead of a z, but you can call it a modified walled test. But because fixed effects, fixed slopes that everybody get, have a null hypothesis of 0 is a reasonable thing, and they can be positive or negative. You don't have to worry about any fancy tests. You can just stare at this p-value. So now my fixed intercept has moved from 19 to 22. It means something different. Previously, in the empty model without time, it was the expected risky behavior at any occasion, the mean. Now it is the predicted risky behavior when time is 0. That happens at age 18. So 22 is the expected outcome at age 18 specifically. The slope then is interpreted the same way as any other type of regression slope. For every, I would say, 1 unit increase in time, but that's lazy, because you know what units are. I would say year in this case. For every additional year, risky behavior is predicted to increase by 1.1, ending up at 22. In terms of effect size, in multi-level models, there's a couple different ways to do it. A most common version is something called pseudo R-square. So I have a couple slides on this, but you can see an example of this. Pseudo R-square is what the variance was before minus what it is now over what it was before. So for instance, I just added time to the model. Is time a time variable or a people variable? Not a trick. Yeah, it's a time variable, right? So is time level 1 or level 2? I love your face. Oh, she's like, I should know this one. Yeah, so time is level 1, people are level 2. So given that time is level 1, which variance should it explain? Level 1 residual or level 2 random intercept? So 1. So if I take the residual variance that I had before, which was the 17 minus 11 that it is now, divided by the 17 that it was, I get this number right here. So this is a little program that I wrote to do these calculations for me. I also have it as a tab in Excel here. So I have this as times 100 to make the decimals a little easier to work with. So 34%. That sounds like a lot, doesn't it? It's impressive. Yes, question? One could center at 12 instead if you wanted to. I was thinking about it down the road in terms of effects that you would put in as a main effect and as an interaction with time. I was more interested in having a main effect that spoke to sort of when the maximum risky behavior would be at the end of the study, but you could certainly change it around, and you can also ask for what the model predicts it to be at any age, and I have example code that shows you how to do that in just a couple pages. So this is what's known as a pseudo R-square. So that's not a name that I made up. That's not me being funny. That's what everybody calls it. Because pseudo R-squares are squirrely. They can go negative sometimes. They can move around for reasons that you cannot explain. But generally speaking, what pseudo R-square means is it's a reduction in each pile of variance specifically. So as many piles of variance as you have in your model, that's how many R-squares you can potentially compute. A level 2 random intercept variance, that's between person mean differences, and we have a level 1 residual variance, which is within person differences. We just got 34% of that level 1 residual variance explained by adding a fixed linear slope for age. And that sounds super impressive until you think about how much was there to begin with. Do you remember how much was there to begin with from the empty model? Well, 39 was the between. So 61, thank you for doing the math for me. I'm always nervous doing math in front of people. So yes, if 39% was between, then 61 is within. So what I'm saying here is that of the 61% that was level 1 within, we just captured 34% of it, 34% of the 61%. Now, what happens at level 2 may be surprising, but it is not unexpected. This pseudo R-square for the random intercept variance is actually negative. That is going to happen. Your level 2 random intercept variance is going to go up whenever your level 1 residual variance is explained. These two numbers are actually yoked together. I have a slide about that gives you the reason why, but this shows what's going to happen. Do you want to hear the reason why, or do you care? Yeah, you care? Okay. Because this is one of those pseudo R-square deals that is crazy, but it's not actually that unexpected. Good, I am streaming. Sometimes I'm like, did I remember that? I'm skipping ahead to that slide. That one. slide 40 in lecture 1. So this is the pseudo R-square that we just looked at, was minus is over was, where we compare the model without the term in question to the model with the new term and look at how much of the targeted variance went down. So what will happen then when you add a fixed effective time or any level 1 predictor that is purely level 1? It will explain the residual variance and in so doing increase the level 2 random intercept variance. The reason is that the model is trying to give you the true level 2 variance, not the observed. So if I took this room and randomly assigned you to groups of, say, 5, and I asked you to calculate the mean height of your groups, assuming random assignment worked, would all of the groups' mean heights be exactly the same? No, they differ a little bit, just because of noise, because of who the groups are. Well, that's what the program thinks too. It's like, well, some of your mean differences are just because of noise, so I'm going to try and give you like your purified estimate of random intercept that's been separated from the noise. And what it thinks noise is residual variance divided by the level 1 sample size. So for example, these are some numbers that came from chapter 5. If I had an observed level 2 random intercept variance just of the person means of 4.65 and a level 1 residual variance of 7, that number, that 4.65, would be given to me as 2.88. It would take the observed level 2 random intercept variance, correct off what it thinks is due to chance, and give me what it thinks is true. Now, if I were to add a fixed linear time slope, and in this case, it reduced the residual variance at level 1 from 7 down to 2 for a 70% reduction. Now, it plugs it into the same equation, but there's less residual variance there to be noise. So it looks like now the random intercept variance at level 2 is higher than it was before. So some of you are staring and some of you are nodding. So this means two things. Number one, don't panic when this happens because you didn't break it. It's going to happen. It's a consequence of how these things are estimated. I wouldn't report that the variance went up. It's not the thing that the model was targeting. If time is purely level 1, then level 1 residual is the effect that it should be targeting, and that's the relevant variance to report an effect size for. However, what happens if age has between person variance in it? What if my study actually started amongst, say, 10 to 15-year-olds, and I measured them for 7 years? Well, then I have a cross-sectional age difference depending on who I sampled at the beginning, what cohort I was in, and a longitudinal age difference as well. In that case, it will make the level 2 random intercept variance go down to the extent that between person differences in age matter, and you'd have to worry about a different between than within person effective age. But this also has implications for what one would do if they get an intra-class correlation from an empty model of 0. So what if reviewer 3 asks you, do you really need like a fancy multi-level model? Well, one way to justify that is say, actually, we tested that. We did a significance test for a model that has a random intercept variance, meaning making it a 2 level, and it fit better. But what if it didn't? What if you'd started out with an empty model where the random intercept variance was close to 0 and so was your intra-class correlation? Does that mean you get to take the afternoon off and not come back, not listen anymore? Nope, because it's going to come back. A random intercept variance of 0 will not stay 0. It will grow after the residual variance at level 1 gets explained. So the intra-class correlation you end up with after you put level 1 predictors in is going to be different than the one you start with. So for that reason, the answer is almost never can I get away with not doing a multi-level model. And that's what keeps me in business. So does that help explain this screwiness here? All right. So yes, the residual variance at level 1 decreased by 34% because we added level 1 fixed time. That decrease in residual variance caused the level 2 random intercept variance to go up. Okay. Other questions? Ooh, lunches. So let's add random linear and see what happens. So my model thus far predicts that everybody changes the same. That's pretty unrealistic. I am now going to add the random slope. I'm going to allow each girl a deviation from the fixed slope. So notice that it shows up twice in the code here. So for instance, in the fixed line of SPSS, I still have age, and I have picked up age on the random. So when you add a random slope, it doesn't mean you take the fixed slope away. You will break the model if you try. It might let you do it, but it would be wrong. Even if the fixed slope is non-significant, it stays, because the random slope is phrased as how far off you are from the fixed slope. So what it's off from needs to be in the model too, for that to make sense. So when we add a random slope variance for time, age in this case, we are also adding a covariance with the random intercept variance that was already there. So in total now, my model for the variance, for the total variance and covariance across time, has 4 things in it. Random intercept variance, which is 21. Random age linear slope variance, which is this 0.57, that's a new one. A covariance between the random intercepts and the slopes, that's the 2 right here. And my level 1 residual. So those are the 4 terms that create the patterns. The rest of this output shows you how those patterns get created. So what's not here is the R matrix that would just have a row of 8s and nothing in the off diagonal. So in, for instance, in building the V matrix that we looked at on this slide, remember this slide? This 8 would go here. 8, 8, 8, 8, 8, 8, 8, 8, 8. Here's my G matrix. There's the correlation version of it. So 21 is the differences between girls in their intercept. And now because I have a random linear time slope, this is the intercept at time 0 specifically. So 21 is the differences between girls at 18 as predicted by the model. 0.57 is the variance in the linear effective age, the collection of U1 offnesses. The end result of this set of matrix operations using each girl's individual Z matrix is printed for you for these data right here. So I want to point out a couple patterns here. So this is the variance at time 12, time 13, time 14. Here's the variance at time 18. That 29 comes from adding together the 8 and the 21. So at this point, we don't calculate interclass correlations anymore, because what this model says is that the interclass correlation is time specific. The one that you would calculate using the random intercept variance and the residual variance is specific to time 0. So here's random intercept plus residual put back together again. These variances are predicted based on the specific time observations that each girl has. So So you'll note the matrix is being printed for the first person in the data set. The next person, who has a slightly different set of time observations, would have a slightly different matrix. But the pattern would be the same in the sense that this model predicts the variance to change quadratically over time. So you'll see this increase in variance as the times go on towards 17 and 18. And it predicts the covariance to change over time, such that occasions closer together are more related than occasions further apart. So all of this with in-person correlation right here, all of that came from random intersubstance slopes. There's no AR1, there's no ARMA, there's no Topolitz, there's no any of that. Whether or not we need any of that is an empirical question by adding things to the R matrix to make it look something other than this structure where everything is zero. If you added something to make it off zero elements, it would change the prediction. So that's what random effects are for. They introduce correlation because your data have correlation. So now the assumptions that we make is not independence, but dependence of this particular pattern. And here's the formula that got it to us. Okay. Now I want to point out something, common misconception. Do you see these p-values here next to my variances? Wouldn't it be nice if I could just look at that and be like, yep, that's not zero. But you know what will happen if I do that? There's like 20 people in the world who know the difference and will yell at you if they happen to be reviewer 3. So these p-values are no good. These p-values are based on a Wald test. The idea that I can take this number, go 2 standard errors around it on either side, and that my variance has a normal sampling distribution. Yeah, nope, I love the emphatic head shake in the back. Yes, variances can't be negative. So this sampling distribution needs to understand that it's up against a wall. The sampling distribution has to stop when it runs into a zero and get truncated, but it doesn't do that. So in general, when you're up against a wall, you can't have a walled test. Thank you, I'm here all week. What do we do instead? Model comparison. So have you seen these before, likelihood ratio tests, -2 log likelihood differences? Some folks. Well, in case you haven't, I have a slide on that. Let me find it. Here we go. Difference in -2 log likelihood between models. It's always fewer minus more, so the difference is positive. You calculate also the difference in the number of parameters, so the number of things you either added or took away, and you compare that -2 log likelihood difference to a chi-square table with those degrees of freedom. So I have a little macro that does that. That's what this little thing is telling us. So -2 log likelihood is what this program gives us. That's what you get in SPSS. In Stata or in M+, you get log likelihood. This is another piece of job security. If you get log likelihood, bigger is better. Log likelihood means taller. Taller data, taller is better. But in order to compare models, you have to take your tallness, log likelihood, and multiply it by -2 to get the direction right and to fit a chi-square distribution. So some programs do you a solid and say, well, how about I just multiply that log likelihood by -2 for you, so then you can just do this just straight subtraction. And so -2 log likelihood is what I'm staring at here, where smaller is better. So the difference between my model that had only a fixed linear term, and one that added a random linear term plus its covariance. That's why it's a difference of 2. The difference in these two numbers right here is 120. And here's a p-value that is 0 up to all of the decimal places SAS prints. So yes, this critical value for 2 degrees of freedom is 6. So yes, 120 is bigger than 6. As another aside, in the book you will see my -2 log likelihood differences, so this delta thing meaning difference, using degrees of freedom with a tilde in front of it. That means ish. Because here's another thing that reviewer 3 might ask you about that I just can't bring myself to care about too deeply. Because variances can't be negative, using a straight up chi-square is not cool. You're supposed to use what's called a mixture chi-square. So instead of having 2 degrees of freedom, you would actually want to have a mixture of 1 degree of freedom when the variance would have been negative but can't, and 2 when it was positive. So the critical value changes if you're in a mixture chi-square from 5.99 to 5.14. For 120, you're good either way. So I just can't bring myself to care, I'm sorry. But if you're somewhere between 5.14 and 5.99 on your test, then you have to care. To ignore it is to be overly conservative. I can live with that. So at this point, I have a note here. We do not calculate pseudo R-square. We do not talk about explained variance when we add random effects, because random effects do not explain variance. They do not explain variable. There's another typo for you. They partition it. So what we've done in adding at random variance and its covariance with the intercept is make another pile. This model now has 3 kinds of variability in it. We have level 2 between person intercept differences, level 2 between person age slope differences, and level 1 within person. So by adding something random, we're not explaining anything. We're just repartitioning what used to be within person residual into what is actually between person differences in slope. Okay. Quadratics are next because this is bendy. All right, how are we doing, folks? Okay. Let me say a couple of things about that before we get to quadratics. Let me answer a question first. I'd love to do that. Certainly. I actually have a slide for that. Can I do my slide instead? I'll say it again. Yeah, this is slide 47. Yeah. This is what we did in pictures. So once upon a time there was an E. Life was simple. We had 1 pile of variance and 1 R-square. First thing we did is make it more complicated. We take what was E and we split it into 2 piles. What we're calling between persons intercept variance at level 2, and what is still E within person variance at level 1. We then added fixed effects of time, and because time is a time-varying predictor, it explained level 1 residual variance. So fixed effects do explain variance. There's less level 1 variance than there was before, and in our example it was 34% less. Then when we add a random effect, what we're asking is part of the reason why you are off your line today because you need your own line? So what was level 1 residual, why are you off your line today, gets partitioned into level 2 slope variance. And there's still residual variance around the individual slopes to be why are you off your line today, so long as you have 3 or more occasions. So what we end up with then are 3 piles of variance. 2 at level 2 that's between persons, and 1 at level 1 that's within persons. That helps? Okay. The nitty-gritty of how to do it correctly is the boring part. The conceptual part is helpful, I think. And the same thing would be true if you had a more complex model. So what if people were nested in groups, for instance? Well, part of what we're calling between person would have to get split here. So this level 2 random intercept variance would have to get split into what is level 3 between group and what is still level 2 within group. And the same thing could happen with the slopes as well. So ultimately, we just keep making piles. We just keep splitting stuff out of piles. So foreshadowing where we're headed next in the example, E variance right here is still, why are you off your line today? Well, what if it's because so far we've drawn straight lines, whereas the answer key model that we started with looked a little bendy? Well, if I add fixed quadratic time, which of my 3 piles should it explain? So I'll make this an easier multiple choice. If I have level 1 fixed quadratic time, should it explain level 1 residual variance or level 2 intercept and slope variance? Yeah, level 1, yeah. So fixed quadratic is going to knock out more of this. But then we have, well, why are you still off your line? Do you need your own bendy? Does everybody need their own differences in curvature? Well, if so, that comes out of here, and that's going to make yet another pile. Then we have 3 between person piles: linear slope, quadratic slope, and intercept. And each of these circles, by the way, can also be thought of as a latent variable. That's why they're circles. Piles. Okay. Yes? Mm-hmm. Okay, so the question is, why does this level 1 within person become this level 2 slope variance? Can I show you another picture that's not in your slides that will answer it better? Okay, 1 second. Last weekend, I was at the University of Illinois, and I still have those materials on my laptop. This one. So this slide is actually meant to show why you can't have random slopes in 2 occasion data, but I think it will answer your question. So in this picture here, this is what a random intercept only model would look like. So in this case, these people are from the same group, same conditional and the same predictors, so they get their own intercept, but they have the same slope over time. And so E is, why are you off your line today? So these are the lines that are drawn from each person. It's a combination of giving them a shared slope, but then their own U0 starting point. And so these E's are off. But you notice if we draw a better line for each person, part of what we're calling off became differences in slope. And with 2 occasions, you can't differentiate that. But once you have more than 2, part of the off can become slope differences, and there would still be residual deviations around the lines. Does that help? Okay. What else can I help with? All right. Stuff that I skipped over that I need to hit besides SEM. REML was a question that I had. Who was the one to talk to me about REML? Who was that? That was you? Okay. Well, then you get another one. So this, comparing -2 log likelihoods. So this is a likelihood ratio test, otherwise known as a lot of other things too. Slide 43. So there are 2 different flavors of maximum likelihood that you will come across in these programs. And they are called ML or REML. ML is maximum likelihood. REML, as I say it, is either restricted or residual maximum likelihood. Not to be extra confusing, but sometimes you will get FIML thrown in there too. FIML stands for full information maximum likelihood, but REML is also full information. But for whatever reason, people never say FREML, whereas they should, because it is. So if you're going to say FIML, you also have to say FREML, and help me make it a thing, okay? But what full information means is that it uses all of the original data to estimate the model rather than a summary thereof. So for instance, limited information would start from a covariance matrix, estimate everything without the original data, which causes problems if you have missing data. Full information uses all the original data. So both REML and ML are full information. The difference has to do with how they compute variances. And it boils down to the same difference that you were taught in intro stat about what the appropriate denominator would be for a sampling variance versus population, whereas n versus n minus 1. N minus 1 is REML, n is ML, the end. Why this matters is that when n is little, when your level 2 sample size for people is small, the difference shows up in your random effects, such that the ones that you get from ML in small samples are going to be too little. The ones that you get out of REML are correct. So if the variances at level 2 are too little, so are the standard errors for the level 2 predictors. So REML is more accurate than ML at estimating variances. It stops mattering after maybe 100-ish level 2 units, I would say, depending on the complexity of the model. But REML is only available in software for univariate multi-level modeling and only available for models that have residuals that are normal at level 1. So everything else in the world is estimated by regular flavor maximum likelihood. Structural equation models, item response models, any kind of factor analysis, all of that is regular flavor. So you only have to care about this distinction if you're working in the world of small samples. Otherwise, you can feel free to ignore it. Unfortunately, M+ does not have REML. So if you want to do any of the multi-level models that are fancier, that are multivariate, like mediation or that kind of stuff, you're stuck with ML or Bayes, which is a whole separate ball of worms. All right. And here is what I just said in a table. M+ only has FIML. It does not have FREML. Yeah, both of them are full information. That's not the distinction. Yes, sir.
So, and I read this before. So, but M+ has RML. They're very clear to not stand for anything like that. So what's the difference? Do you know what the difference between RML and REML is?
I do not. I would have to look that up. I haven't seen the RML, but yeah, it doesn't have REML. All right. Yeah, I think that's about all I need to say about that. So we can talk about quadratics and such after lunch, because it's time to eat. So help yourselves, and we'll be back.
An hour?
Yeah, hour and 10 minutes, I think. Yeah, 110? Yeah. Sorry, I went a bit over in my enthusiasm.